Today we're going to be graphing derivatives of rational functions. So one more time, just open up desmos.com/calculator on your browser and put in the equation of the function f of x equals 4x over x squared minus 9. And you should get this graph. And you can give a quick sketch of it on your handouts. So you can see the function graph on Desmos. So once you're done sketching it on your handout, you can also just type in f prime of x. And it's a little bit confusing to see both graphs at the same time. So if you just click on the color icon next to f of x, the graph of f of x will disappear, and you can just sketch the derivative function on the second grid on your page. And then repeat that one more time for f prime prime or f double prime of x. And again, click on the icon, the colored icon next to f prime, and that graph will disappear. And then the one that's remaining is the second derivative. Okay, so sketch all three functions on your page. Okay, now, based on the graph of the function, you can state the coordinates of the point of inflection for this function. When we look at the original function here, we can see that the function is always concave down when x is less than -3. And then here we have concave up and then changes to concave down. So it looks like the point of inflection based on our graph is going to be at 0, 0. Okay? And then at x is greater than 3, the graph is always concave up. So again, we're going to complete this investigation by looking at each of the graphs and figuring out what's happening on each interval. So when x is less than -3, the function is decreasing. At -3, we have an undefined value. That's where we have a vertical asymptote. From -3 to 0, the function is, again, decreasing. At x equals 0, still decreasing. And then when x is between 0 and 3, still decreasing. Then at x equals 3, we encounter another undefined value, so another vertical asymptote. And then when x is greater than 3, we will have, again, the function is decreasing. So that was all based on f of x. Just to reiterate, all of this that I've just gone over on the first row of the table, that's all based on the original function, f of x. So let's repeat this for the first derivative. Okay. So we can see that the graph of the first derivative shows us that when x is less than -3, the derivative is negative. At -3, the derivative does not exist. We have vertical asymptote. Okay, from -3 all the way to x equals 3, we have the derivative is negative. At x equals 3, again, the derivative does not exist. And then when x is greater than 3, the derivative is still negative. So that matches what we know based on the fact that the function was decreasing, derivative is negative, undefined, derivative does not exist, right? So now let's repeat this investigation one more time for the second derivative. Okay, the third row I'm completing based on the second derivative here. So the second derivative is negative when x is less than -3, does not exist at x equals -3, and then it's positive when x is between -3 and 0. At x equals 0, the second derivative is 0. And when x is between 0 and 3, the second derivative is negative. And then at x equals 3, the derivative does not exist because of the vertical asymptote. And then when x is greater than 3, the second derivative is back to positive. And then based on the second derivative, we can conclude that the overall function is concave down when x is less than -3. Undefined at x is equal to -3. Concave up from -3 to 0. And at x equals 0, we have our point of inflection. Then when x is between 0 and 3, the graph is concave down. At x equals 3, undefined. And then when x is greater than 3, concave up. Okay, so let's move on to the next page and answer some questions based on what we just figured out. Explain the behavior of the function f of x at the points where x equals -3 and x equals 3. We saw that we had vertical asymptotes at x equals -3 and x equals 3. So basically, the limit as x approaches -3 of f of x did not exist, and the limit as x approaches 3 of f of x also did not exist. Okay, the second question is, are 3 and -3 considered critical numbers? And if you go back to our very first lessons about local extrema, we define critical numbers as those that are within the domain of the original function. So they are not considered critical numbers because x equals plus minus 3 are not in the domain of the original function. Now, how do the circled results in the chart confirm the answer that we've stated in B about the location of the point of inflection? Well, we see that, if I just quickly flip back to that page, at x equals 0, the function is still defined, right? F of x was decreasing at that point. Okay. The first derivative was negative, and then the second derivative was 0. And then on either side of the second derivative being 0, we can see that the sign changes from positive to negative. So that's how we know that we have a point of inflection at x equals 0. Okay. So in part G, we're going to go back, do a little bit of review, and see which of these applies to the function f of x equals 4x over x squared minus 9. So first of all, the increasing or decreasing test, this would be based on the first derivative being positive or negative. And we did find that when f prime is positive, the function is increasing, and when f prime is negative, the function should be decreasing. And this is the only result that we saw. The function was always decreasing on its domain. Okay. The next one, the first derivative test, if you recall, is all about finding local extrema. And in this case, we had to figure out where the derivative is equal to 0 or does not exist, even though the original function at that point does exist. And this did not come up in our results. The first derivative was always negative. Okay? And that meant that we had no local extrema, which if you look back at the graph of the function, you will see that we don't have any local or relative max or min points. The next part is the concavity test. This is using the second derivative to figure out whether the function is concave up or concave down based on the second derivative being positive or negative. And we did see that in the last two rows of the investigation. We saw that when f double prime was positive, then we had the function be concave up. And when the second derivative was negative, then the function was concave down. And last but not least, the second derivative test, again, this is to figure out local extrema. This was where we could figure out if f prime was equal to 0 and f double prime was negative. Then we had a function be concave down, so that meant that we had a local maximum. And then if f prime was 0 while the second derivative was positive, then we had a local minimum. But this test did not apply because we did not have any local or relative extrema. So now that we have we've done this investigation with graphing rational functions and looking at how the asymptotes will translate into the first and second derivative, we're going to apply this knowledge along with the curve sketching algorithm to accurately sketch the graphs of rational functions.